Today we're diving into the fascinating world of multilayer perceptrons, or MLPs, one of the key building blocks of modern artificial intelligence. But before we jump in, let's take a step back. Imagine trying to recognize a friend in a crowded room. Your brain doesn't just take a single glance and make a decision. It processes patterns, compares features, and refines its understanding. That's exactly what MLPs do in AI, but with numbers instead of faces. So what's on the agenda? First, we'll look at why single-layer perceptrons just don't cut it for complex tasks. Then, we'll break down the architecture of an MLP, input layers, hidden layers, output layers, how each one plays a role. We'll touch on the universal approximation theorem, which basically says MLPs can approximate any function given the right setup. Then, we'll tackle a common debate. Should networks be deep and narrow or shallow and wide? Of course, an MLP is nothing without activation functions, sigmoid, TNH, ReLU, which determine how neurons fire and influence learning. We'll explore how backpropagation fine-tunes these models through training and how optimization techniques like stochastic gradient descent help speed things up. But with great power comes great responsibility. MLPs can overfit, struggle with vanishing gradients, or require massive datasets. And if you think MLPs are the only game in town, think again. We'll compare them to convolutional neural networks, CNNs, for image tasks, and recurrent neural networks, RNNs, for sequential data. Finally, we'll gaze into the future. Where are MLPs headed? How are they evolving with attention mechanisms, dynamic architectures, and real-time processing? But let's not get ahead of ourselves. Before we can predict the future, we need to understand the foundations. And that starts right now. Ready? Let's talk about something that's at the heart of artificial intelligence, something that makes machines think in a way that almost feels human. Multilayer perceptrons. Sounds complicated, right? But don't worry, we're going to break this down in a way that actually makes sense. Imagine you're training a dog. If you only teach it one trick, like sitting when you wave a treat. Sure, it's smart, but it's not exactly impressive. Now, imagine you teach it to sit, roll over, play dead, fetch your slippers, and even bring you coffee. That's next-level intelligence. That's what happens when we go from a simple perceptron to a multi-layer perceptron. It stops being a one-trick pony and becomes a full-fledged AI powerhouse. MLPs are the backbone of machine learning, helping computers recognize images, understand speech, recommend your next Netflix binge, and even diagnose diseases. Without them, AI would still be in the digital Stone Age. But here's the thing. Single-layer perceptrons, they have serious limitations. They're like a toddler playing tic-tac-toe. They get the basics but fail at anything even remotely complex. So how do we fix that? How do we take neural networks from meh to mind-blowing? That's where the magic of multiple layers comes in. And here's the best part. MLPs have a superpower. They can approximate any function given enough layers and neurons. That means they can learn patterns so complex that even humans struggle to explain them. It's like teaching a robot to see the world the way we do, but even faster. So how exactly do they work? What makes them so powerful? And why are they considered the universal approximators of AI? Well, that's what we're about to uncover. Get ready, because once you understand this, you'll never look at AI the same way again. Let's be honest. Single-layer perceptrons are kind of like those old-school flip phones. They were cool when they first came out, but compared to today's smartphones, completely outdated. Sure, they could make calls, send texts, and even play a few pixelated games, but try running Google Maps on one of those things. It's just not happening. That's exactly the problem with single-layer perceptrons. They do one thing, and they do it in the simplest way possible, but the moment you ask them to handle anything remotely complex, they crash and burn. Let's break this down. The biggest problem with single-layer perceptrons is that they can only handle problems where the data can be separated by a straight line. That means if you're working with data that forms nice, clean categories like separating apples from oranges based on color alone, it might work. But real-world data? It's messy. Patterns are complicated. Relationships between inputs aren't always so obvious. Imagine trying to classify emails as spam or not spam using just one feature, like the number of capital letters. Sure, all caps emails might look spammy, but what about the subtle ones? What about phishing emails that look just like real messages? A simple rule isn't going to cut it. This is the fundamental problem. Real life isn't linear, and because single-layer perceptrons are stuck with straight-line thinking, they completely fail when the patterns become even slightly complex. They can't recognize handwriting, they can't tell a cat from a dog unless the difference is painfully obvious, and they certainly can't process language the way humans do. Let's take an example. Imagine you're designing a basic AI to tell the difference between different emotions in photos. If you used a single-layer perceptron, it might just look at one feature, say, whether someone's mouth is turned up or down. If it's up, it says happy. If it's down, it says sad. But what about surprise? What about fear? What about someone smiling sarcastically? The real world doesn't work like that, and that's why single-layer perceptrons fail in situations where deeper understanding is needed. Another massive limitation: no hidden layers. Think of hidden layers like the backstage crew in a theater production. The actor's input layer and the audience output layer might be the ones in the spotlight. But without the hidden crew setting up the props, adjusting the lighting, and making sure everything runs smoothly, the entire show falls apart. Hidden layers help refine the information, detect patterns, and make sense of the input before passing it to the output layer. Without them, the perceptron is just guessing based on surface-level details. Let's take another real-world analogy. Imagine teaching a kid how to recognize animals. You show them a picture of a dog and say, "This is a dog." Then you show them a picture of a wolf and they confidently say, "Dog." Why? Because at a surface level, wolves and dogs look similar. But if the kid had an extra hidden layer in their thinking, they might look at extra features. The shape of the snout, the size of the body, the expression in the eyes, and start to understand the deeper differences. That's exactly what hidden layers do in MLPs. They allow the network to go beyond the obvious and recognize complex patterns. And here's where things get even worse. Single-layer perceptrons aren't just limited in what they can learn, they're also extremely inefficient when dealing with real-world problems. Let's say you're trying to train an AI to recognize handwritten numbers. With a single-layer perceptron, you'd need a ridiculous number of individual rules. One for every possible variation of the number 8, one for every weird way people write 4, and so on. It's like trying to memorize every single street in a city instead of just learning how to read a map. A multi-layer perceptron, on the other hand, learns from patterns. It doesn't need to memorize every variation of the number 8. It just understands the concept of eightness based on multiple layers of refined learning. And let's not even talk about noise. In the real world, data isn't perfect. Maybe you're analyzing speech patterns, but there's background noise. Maybe you're training a medical AI, but some images are blurry. A single-layer perceptron would be completely lost. But with more layers, an MLP can filter out the noise, focus on what really matters, and make sense of the chaos. So, to sum it up, single-layer perceptrons are like trying to solve a Rubik's Cube while only being allowed to rotate one side. You might make some progress, but you'll never actually solve the puzzle. They just don't have the depth, flexibility, or intelligence to handle complex problems. But the good news, we can fix this. We just need more layers, more depth, more intelligence. And once we start adding those hidden layers, everything changes. And that's exactly where we're headed next. Because once you understand how layers work, you'll see why MLPs are the real brains behind modern AI. So we've established that single layer perceptrons are like flip phones, useful in their time, but nowhere near powerful enough for today's AI challenges. So what's the upgrade? Multilayer perceptrons, or MLPs. Think of them as the smartphones of machine learning, packed with power, capable of multitasking, and able to process way more information than their older counterparts. But how exactly do they work? What makes an MLP different from a simple perceptron? Let's break it down. Imagine building a detective team to solve a mystery. A single layer perceptron is like hiring one detective who makes a decision based on a single clue. Not great, right? An MLP, on the other hand, is like assembling an entire team. One detective gathers fingerprints, another analyzes alibis, another checks security footage. They all contribute their insights before coming to a final conclusion. That's how MLPs process information, in layers, each one refining and improving the data before passing it forward. The first layer is the input layer, the starting point. This is where raw data enters the network. Each neuron here represents a single feature from the dataset. If we were building an AI to recognize handwritten digits, for example, every pixel in the image would be a separate neuron in the input layer. The more features we have, the more input neurons we need. Think of this as gathering all possible clues before starting the investigation. Next, we move to the hidden layers, the real brains of the operation. These layers don't just pass information forward, they transform it, learning patterns, extracting key features, and making sense of complexity. If the input layer is a raw image, the hidden layers are where the magic happens, where the AI figures out edges, shapes, curves, and ultimately what digit it's looking at. The more hidden layers, the deeper the network, and the more powerful it becomes. Now, here's where it gets interesting. Each neuron in a hidden layer is connected to every neuron in the next layer. It's like a giant web of connections, where each node assigns a weight to the information it receives. The AI tweaks these weights over time, strengthening the important ones and ignoring the weak ones, just like how we learn by refining what's important and discarding what isn't. If a hidden layer detects that a curve is important in recognizing the number 8, it will reinforce that signal, making future predictions more accurate. And then finally, we reach the output layer, the decision maker. This is where the network spits out a final prediction. If we're building a classifier, the output layer might have 10 neurons, one for each digit 0 to 9. The network assigns probabilities to each one, and the neuron with the highest probability wins. If the AI is 92% sure that the number is an 8, that's what it predicts. But what happens if the prediction is wrong? This is where learning comes in. The network backtracks through the layers, adjusting its weights to improve future accuracy. It's like a detective realizing they misinterpreted a clue and going back through the case notes to correct their mistake. This process, called backpropagation, is what makes MLPs so powerful. They don't just make predictions, they learn, adjust, and get better over time. And here's a fun fact. MLPs are universal approximators. That means given enough neurons and layers, they can approximate any function, no matter how complex. It's like having a math genius who can solve any problem thrown their way as long as they have enough time to figure it out. But here's the big question. How many layers do we actually need? Can we just keep adding more and more for better performance? Well, not exactly. Too few layers and we don't capture enough complexity. Too many and we run into problems like overfitting and excessive computation time. It's a delicate balance, one that AI researchers are still optimizing to this day. So, what's next? Now that we know the structure of an MLP, we need to talk about why it actually works. Why can a network with just a few layers approximate any function? How do we know it won't just fail like a single layer perceptron? That's where the universal approximation theorem comes in. And trust me, you'll want to hear this. Now we're getting into some seriously cool territory. We just talked about how MLPs are structured. Input layers, hidden layers, output layers, all working together like a well-oiled machine. But now, let's take a step back and ask the big question. Why do MLPs even work? I mean, it's one thing to say, hey, let's stack a bunch of layers together and hope for the best. But how do we actually know that this system can learn anything meaningful? What makes a multi-layer perceptron so much more powerful than a single-layer perceptron? Well, that's where the universal approximation theorem comes in. And if you've never heard of this before, buckle up, because this one's a game changer. Here's the idea in the simplest possible way. Given enough neurons and the right activation functions, an MLP can approximate any function. And I mean any function. It doesn't matter how complex, how weird, how nonlinear. It can be a stock market trend, a medical diagnosis pattern, or even the sound of your voice. Yes, if there's a relationship between inputs and outputs, an MLP can learn it. Think about that for a second. It's like saying no matter what the problem is, an MLP can figure out a way to solve it. That's huge. It means that theoretically MLPs have no limits. If you give them enough time, data, and computational power, they can model anything. But hold on. How does that actually work? Let's break it down. Imagine you're trying to draw a really complex curve. You start with a straight line. It's a bad approximation, right? But then you add another line and another, adjusting the angles slightly each time. The more lines you add, the better your approximation gets. Eventually, if you add enough tiny lines, you can get so close to the real curve that the difference becomes invisible. That's exactly how MLPs work. Each layer, each neuron adds a little more detail to the function it's learning. Given enough neurons and layers, the network can get so good at modeling a function that it becomes practically indistinguishable from the real thing. Mathematically speaking, this was proven in the late 1980s. Researchers showed that even with just one hidden layer, an MLP with enough neurons can approximate any continuous function. That's a big deal because it tells us that depth isn't always necessary. Sometimes just having a lot of neurons in a single hidden layer can be enough. But in practice, deeper networks tend to learn faster and generalize better, which is why deep learning has taken off. But here's the catch. Just because an MLP can approximate anything doesn't mean it will automatically learn the right function. It still needs to be trained properly, and that means using the right number of layers, neurons, and activation functions. It also needs good data, because if you feed it garbage, it'll learn garbage. That's why designing an MLP isn't just about stacking as many layers as possible. It's about understanding how many layers and neurons are actually needed to learn the function efficiently. And here's another fun twist. More layers don't always mean better learning. Sometimes adding too many neurons leads to something called overfitting, where the model becomes too good at memorizing training data, but completely fails when faced with new inputs. It's like a student who memorizes every word in the textbook, but can't answer a real-world question because they never actually understood the concepts. So, where does that leave us? The universal approximation theorem tells us that MLPs have the theoretical power to solve any problem, but in the real world, it's all about designing them the right way. So now that we know an MLP can learn any function, the next big question is, how do we build one efficiently? Do we go for a wide network with tons of neurons or a deep network with many layers? Well, that's a debate researchers have been having for years. And the answer? It's not as straightforward as you might think. Let's dive into that next, because the choice between long and thin versus short and fat architectures can make or break your neural network. And you might be surprised at what actually works best. All right, so we've established that multi-layer perceptrons are powerful. They can approximate any function given enough neurons and layers. But now comes the million-dollar question, what's the best way to build one? Should we go for a deep and narrow network, long and thin, or a shallow and wide one, short and fat? This might sound like an engineering decision, but it's actually a fundamental debate in AI. And trust me, the answer is not as straightforward as you might think. Let's start with short and fat networks. These are networks with fewer layers, but a large number of neurons per layer. Think of them like a big brain with a simple thought process. They try to capture as much information as possible in a single go. It's kind of like trying to learn how to cook by watching a single 10-hour YouTube tutorial instead of practicing step by step. You might learn something, but you're not really building a structured understanding. The problem with short and fat networks is that they're great at memorization, but terrible at generalization. If you throw enough neurons at the problem, the network will eventually memorize patterns in the training data, but when faced with something new, it completely falls apart. It's like cramming for an exam and forgetting everything the next day. Not ideal, right? Now let's talk about long and thin networks. These are deep networks with more layers, but fewer neurons per layer. These are like students who take the time to learn step by step, slowly building up their understanding over time. Instead of trying to process all the information in one go, they break it down into smaller, more manageable pieces. Why does this work better? Because depth adds power. Each layer refines and transforms the data, making it easier to recognize complex patterns. In fact, deep networks are often better at generalization, meaning they don't just memorize, they actually understand. It's why deep learning has become the gold standard in AI. Let's put this in real-world terms. Imagine you're learning to play the piano. A short and fat approach would mean trying to play an entire song on day one, hoping to get it right through brute force. A long and thin approach, on the other hand, would mean starting with scales, learning chords, practicing finger positioning, building up your skills gradually. Which method do you think works better? And here's where things get really interesting. Research suggests that long and thin networks often outperform short and fat ones. In fact, deep networks have been shown to require fewer neurons overall to learn complex patterns, meaning they're not just more effective, but also more efficient. But hold on, does this mean we should just keep making networks deeper and deeper? Not quite. There's a catch. If a network gets too deep, it can run into problems like the vanishing gradient problem, where information gets lost as it travels through layers. It's like playing a game of telephone where the message gets more distorted at each step. This is why researchers use tricks like batch normalization, residual connections, and real U activations to help deep networks learn properly. So, what's the takeaway? In most cases, long and thin networks work better than short and fat ones. But you can't just blindly stack layers forever. You need to find the right depth for your problem. It's all about balance. And now that we know how to structure an MLP, let's take things even deeper, literally. Because the key to making these networks truly learn lies in something even more important: activation functions. And that's exactly what we're going to explore next. Okay, we've talked about layers, neurons, and network structure, but now it's time to talk about something that really brings neural networks to life: activation functions. Think of activation functions as the brain cells of an MLP. Without them, our neurons would just be mindless number crunchers passing values around with no real intelligence. So, what exactly do they do? Simple. Activation functions decide whether a neuron should fire or not. They take an input, process it through a mathematical function, and output a transformed value that determines the neuron's response. Without them, a neural network would just be a glorified calculator, multiplying numbers together without ever learning anything meaningful. Let's put it this way. Imagine you're driving a car. The activation function is like the gas pedal. It controls how much power or influence a neuron has in the decision-making process. If the function is weak, the neuron barely contributes. If it's too aggressive, it can overpower the learning process. That's why choosing the right activation function is crucial for getting an MLP to learn properly. Now let's look at some of the most popular activation functions and why they matter. First up, the sigmoid function. This one's like the grandfather of activation functions. It takes an input and squashes it into a range between 0 and 1. Sounds useful, right? Well, kind of. Sigmoid was great in early neural networks, but it has a major flaw. It suffers from the vanishing gradient problem. This means that when neurons receive extreme input values, the function flattens out, making it really hard for the network to learn. Think of it like trying to sprint in knee-deep water. You can still move, but it's frustratingly slow. Next, we've got the tan function, short for hyperbolic tangent. It's similar to sigmoid, but it ranges between 1 and 1 instead of 0 and 1. Why is this better? Because it's zero-centered, meaning it can handle negative values better, leading to faster learning. But it still suffers from the vanishing gradient issue, making it less ideal for deep networks. And then we get to the superstar ReLU, rectified linear unit. This is the function that revolutionized deep learning. Instead of squashing values like sigmoid or tanh, ReLU just says, if the input is positive, keep it. If it's negative, set it to 0. Simple, right? But here's the magic. This makes training way faster and helps solve the vanishing gradient problem. Imagine running on a treadmill where every step gives you an extra boost. That's what ReLU does for neural networks. Of course, nothing is perfect, and ReLU has its own issue. Sometimes neurons can get stuck with a value of 0 and never activate again. This is known as the dying ReLU problem, and it can lead to dead neurons that contribute nothing to learning. To fix this, researchers introduced variants like leaky ReLU, which allows small negative values instead of outright zeroing them out. So, which activation function is best? Well, that depends on the problem. If you're working with shallow networks or probability-based outputs, sigmoid or tanh might still work. But for deep learning, ReLU, or one of its variants, is usually the best choice. And here's a fun fact. Activation functions are the reason deep learning even works in the first place. Without them, an MLP would just be a linear model, meaning no matter how many layers you add, it would still only be able to learn straight-line relationships. Activation functions break that limitation, allowing networks to learn complex nonlinear patterns, things like recognizing faces, understanding speech, or even generating art. So we've seen how activation functions bring neurons to life. But learning doesn't just happen by flipping activation switches. The real magic comes from training the network, adjusting weights, fixing mistakes, and refining predictions over time. And that's exactly where we're headed next, because now we need to talk about the process that actually teaches MLPs how to think, training and optimization. Okay, now we're getting to the good stuff. How do we actually train an MLP? Because right now it's just a fancy pile of neurons and activation functions. It's like having a brand new smartphone with no apps installed. It looks cool, but it doesn't do anything useful yet. Training an MLP is all about teaching it to make better predictions over time. Imagine you're learning to play basketball. The first time you take a shot, you completely miss the hoop. But you adjust. Maybe you aim a little higher, maybe you put a little less force on the ball. Over time, with enough practice, you start sinking shots consistently. That's exactly how an MLP learns, by making predictions, checking how wrong it is, and adjusting its internal settings to improve. The training process happens in 4 key steps. First, we have data preprocessing, the warm-up. Before we even start training, we need to prepare the data. This means normalizing or standardizing input features so that they're on a similar scale. Why? Because if one feature, like height in centimeters, is much larger than another, like age in years, the model might overemphasize the bigger numbers, leading to bad learning behavior. We also split our data into training, validation, and test sets, because we don't just want the model to memorize the data, we want it to generalize to new, unseen inputs. Next comes forward propagation, the first shot at predicting something. Here's what happens. Input data enters the network, flows through the layers, and reaches the output. Each neuron applies its weights, activations happen, and boom, out comes a prediction. At this stage, the MLP has no clue if the prediction is good or bad. It's just making its best guess based on random initial weights. Then comes the real learning, backpropagation. This is where the network checks how far off its prediction was. It calculates an error using something called a loss function. Think of this as the scoreboard in a basketball game. It tells us how badly we missed the shot. The goal, minimize that error. So how do we do that? By adjusting the weights. Backpropagation works by sending this error backward through the network, telling each neuron how much it contributed to the mistake. Each neuron then updates its weights so that next time the prediction is a little better. This process happens over and over, making small corrections until the network gets really good at predicting. And finally, we have optimization, which is all about making training faster and more efficient. The key tool here is gradient descent, an algorithm that tweaks the weights to minimize the error. Think of it like adjusting your aim in basketball. If you miss to the left, you aim a little more to the right. The most common variation is stochastic gradient descent, SGD, where the network updates weights after every training example instead of waiting for the entire dataset. This makes learning faster but a bit noisier, kind of like taking lots of tiny steps toward the right answer instead of one big leap. And of course, there are advanced optimizers like Atom, which adapt the learning rate dynamically so the network learns faster early on and slows down once it gets close to the best solution. These optimizers are the secret sauce behind modern deep learning, making training smoother and way more efficient. So, to sum it up, training an MLP is all about feeding it data, making a guess, checking how wrong it is, and tweaking the weights to improve next time. Do this a few million times, and suddenly your model is predicting stock prices, translating languages, or recognizing faces better than you can. But of course, there's more to the story. Just because a model can learn doesn't mean it always learns the right things. Training isn't just about making predictions, it's about making the right adjustments. And that brings us to one of the most important parts of training, the backpropagation algorithm. And trust me, you'll want to understand this, because without backpropagation, machine learning as we know it wouldn't even exist. All right, now we're getting into the real magic behind how neural networks learn backpropagation. If training a multilayer perceptron is like learning to play basketball, then backpropagation is the coach that tells you what you did wrong and how to fix it. Without it, the network would just keep making random guesses with no way to improve. So, what exactly is backpropagation? Let's break it down in the simplest way possible. Imagine you're playing darts. You throw your first dart and it lands way off the bullseye. What do you do next? You analyze the mistake. Maybe you threw too hard. Maybe you aimed too high. Then you adjust and try again. That's exactly how backpropagation works in an MLP. The network makes a prediction, checks how wrong it is, and then adjusts its internal settings, weights, to get better on the next attempt. It all starts with forward propagation. The input data flows through the network layer by layer until it produces an output. But at this point, the network doesn't know if it made a good or bad prediction yet. That's where the loss function comes in. A loss function measures how far off the network's prediction was. If it was spot on, the loss is low. If it was way off, the loss is high. The goal of training is simple. Minimize the loss function as much as possible. Now, here's where backpropagation kicks in. The network takes the error and sends it backward through all the layers, figuring out exactly how much each neuron contributed to the mistake. This is done using the chain rule from calculus. Don't worry, you don't need to memorize the math, but the idea is that each weight is adjusted proportionally to how much it influenced the error. Let's break this down with an analogy. Imagine you're running a restaurant and one night the customers are unhappy with their food. You need to figure out why. Is it the quality of ingredients, the way the chef cooked it, the way the server presented it? You don't just fire everyone, you pinpoint the exact issue and fix only that part. That's what backpropagation does. It traces the mistake back to the source and makes precise adjustments to improve the outcome. The way it makes these adjustments is through gradient descent, a fancy way of saying small, controlled changes in the right direction. The network takes a tiny step toward the right answer, updates the weights, and then tries again. This happens over and over millions of times until the network becomes really good at making accurate predictions. Now, why does this work so well? Because backpropagation allows MLPs to learn from experience. Just like a human refining their skills, an MLP continuously adjusts and improves, and the more training data it sees, the smarter it becomes. But, of course, backpropagation isn't perfect. If the learning rate is too high, the network can overshoot the best solution and never settle down. If it's too low, the network learns painfully slowly. That's why modern optimizers like Adam have been developed, to make learning smoother and more efficient. And here's a fun fact. Without backpropagation, modern AI wouldn't even exist. This one algorithm is responsible for the entire deep learning revolution, from self-driving cars to chatbots to medical AI. It's that important. But there's a catch. Just because a network can learn doesn't mean it always learns the right thing. If you're not careful, an MLP can become too good at memorizing training data, which leads to a huge problem called overfitting. And trust me, overfitting is every AI researcher's nightmare. So before we celebrate, we need to understand how to stop our network from memorizing instead of actually learning. Because if we don't fix this, all our training could be completely useless. Let's talk about that next. All right, let's talk about one of the biggest problems in training neural networks, overfitting. If you've ever crammed for a test, memorized every word in the textbook, and then completely blanked when the questions were phrased differently, you already know exactly what overfitting is. Overfitting happens when a neural network gets too good at learning the training data, so good that it memorizes every little detail, including random noise and outliers. The result? It performs perfectly on training data, but fails miserably on new, unseen data. It's like a student who memorizes the answers to practice questions, but has no actual understanding of the subject. Why does this happen? Because MLPs are extremely powerful. With enough neurons and layers, they can learn anything, even the weird, meaningless fluctuations in data. And that's a problem, because in the real world, data is noisy. There are outliers, mistakes, and irrelevant patterns that we don't want our model to learn. If an MLP learns every little detail, it loses its ability to generalize to new situations. Think of it this way. Imagine teaching a child how to recognize cats. If you only show them 5 pictures of cats, they might learn exactly what those 5 cats look like. But the moment they see a cat that looks slightly different, they get confused. That's overfitting. What we really want is for the child to understand the concept of a cat, pointy ears, whiskers, fur, tail, so that they can recognize any cat, even if they've never seen that specific one before. So, how do we prevent overfitting? Regularization. This is a set of techniques designed to stop the network from memorizing the training data and instead force it to learn general patterns. One of the most common regularization techniques is dropout. Dropout is like a mental workout for your neural network. It randomly turns off some neurons during training, forcing the model to learn in a more robust way. Imagine learning to ride a bike, but sometimes you're forced to pedal with just one leg. It's harder at first, but in the end, you become a stronger cyclist. That's what dropout does to an MLP. It forces the network to become less reliant on specific neurons, making it more flexible and better at generalizing. Another method is L2 regularization, also known as weight decay. This works by slightly penalizing large weights, encouraging the network to keep its learning simple. Think of it like a teacher telling a student, don't overcomplicate your answer, just focus on the main idea. The network is encouraged to avoid extreme values, which helps prevent memorization of noise. And then there's early stopping, which is exactly what it sounds like. Instead of training the model for a fixed number of epochs, we monitor its performance on a validation set. The moment it starts getting worse on unseen data, a sign of overfitting, we stop training. It's like studying for an exam. You don't want to overdo it to the point where your brain is overloaded with unnecessary details. So what's the takeaway? Overfitting is a huge problem, but with the right regularization techniques, we can train MLPs that actually understand patterns rather than just memorizing examples. And now that we know how to keep our models from overfitting, it's time to dive into hyperparameters, the secret settings that control how an MLP learns. Because if you don't tune these correctly, your model might never reach its full potential. And trust me, some of these choices can make or break your neural network. Let's talk about that next. Good. So we've built our MLP, chosen our activation functions, trained it with backpropagation, and even tackled overfitting with regularization. But now we're facing the final boss of training a good neural network, hyperparameters. Hyperparameters are like the secret settings that control how an MLP learns. They're not learned by the network itself. Instead, we choose them before training even begins. And here's the tricky part. Small changes in hyperparameters can completely change how well a model performs. Think of hyperparameters like setting up a car for a race. Do you use soft tires for better grip or hard tires for durability? Do you adjust the suspension for tight corners, or do you prioritize speed on straightaways? Choose the wrong settings, and it doesn't matter how skilled the driver is, the car won't win. That's exactly how hyperparameters work in an MLP. If they're set too high or too low, the network will either fail to learn or overcomplicate things and get stuck. Let's break down the most important hyperparameters and how they affect learning. First up, the learning rate, arguably the most important hyperparameter of all. This controls how big of a step the network takes when updating its weights. If the learning rate is too high, the network bounces around wildly, never settling on a good solution, like trying to fine-tune a telescope by shaking it. If it's too low, learning becomes painfully slow, like trying to climb a mountain by taking baby steps. Finding the right learning rate is crucial. That's why modern optimizers like Adam dynamically adjust the learning rate during training to get the best of both worlds. Next, we have the number of layers. Too few layers, and the network doesn't have enough depth to learn complex patterns. Too many, and we run into issues like vanishing gradients or overfitting. It's all about finding the right balance for the task at hand. Closely related is the number of neurons per layer. More neurons mean more processing power, but also more risk of overfitting if the network memorizes patterns instead of generalizing. A common approach is to start with a power of 2 AGM32, 64, 128 neurons per layer and fine-tune based on performance. Then there's batch size, how many examples the network processes before updating the weights. Small batch sizes, like 16 or 32, introduce randomness, helping the model generalize better. Large batch sizes, like 256 or more, make training smoother but can lead to overfitting. It's like studying for an exam. Do you cram small bits of information in short bursts or study everything at once? The answer depends on the task. Another big one, the number of epochs. This determines how many times the model sees the entire training dataset. More epochs allow the model to refine its learning, but train too long and you risk overfitting. This is where early stopping comes in. It watches the validation loss and stops training when performance starts to decline. And finally, momentum. a trick used in optimizers to help the model escape bad local minima. Imagine you're pushing a heavy box. At first, it's slow, but once it gets moving, it builds momentum and becomes easier to push. Momentum in MLPs works the same way. It helps learning move faster by carrying weight updates from previous steps. So, what's the takeaway? Hyperparameter tuning is both an art and a science. There's no one-size-fits-all setting, which is why researchers use techniques like grid search, random search, and Bayesian optimization to find the best combinations. And once you get the hyperparameters right, MLPs can do some seriously impressive things. Want proof? Let's take a look at real-world applications where MLPs are being used today to transform industries from healthcare to finance to entertainment. Because once you see what these networks are capable of, you'll never look at AI the same way again. All right, we've built our MLP, fine-tuned its hyperparameters, and trained it to recognize patterns. But now comes the fun part. What can we actually do with it? Because trust me, MLPs are more than just theoretical math puzzles. They're everywhere, powering some of the most advanced technologies you use daily. Let's start with something you probably use all the time: recommendation systems. Ever wonder how Netflix always seems to suggest the perfect show, or how Spotify creates a playlist that matches your mood? That's MLPs at work. They analyze your watching and listening habits, compare them to millions of other users, and predict what you'll enjoy next. It's basically a neural network acting as your personal assistant, constantly learning from your behavior to fine-tune its suggestions. Now, let's take it up a notch. Healthcare diagnostics. Imagine a world where AI can detect diseases before doctors even spot the symptoms. MLPs are already being used to analyze medical images, detect anomalies in X-rays, and even predict the likelihood of diseases like cancer based on patterns in patient data. In some cases, these AI models outperform human doctors because they can process massive amounts of data and detect subtle patterns that might go unnoticed. And speaking of high-stakes decision-making, finance is another field where MLPs are making a huge impact. From predicting stock market trends to assessing credit risk and detecting fraudulent transactions, these networks are helping banks and investment firms make smarter, faster decisions. If you've ever received a fraud alert from your bank, there's a good chance an MLP was behind it, analyzing thousands of transactions per second to flag anything suspicious. But it doesn't stop there. MLPs are also revolutionizing natural language processing, NLP. Ever used Google Translate? Talked to a chatbot? Typed a message and had your phone predict the next word? That's MLPs working behind the scenes. They help machines understand and generate human language, making interactions between humans and AI more natural and intuitive. And of course, we can't forget image recognition. MLPs are used in everything from facial recognition software to self-driving cars. They help security systems identify people, assist autonomous vehicles in detecting pedestrians, and even power augmented reality filters on social media apps like Instagram and Snapchat. The best part? We're only scratching the surface. As AI technology continues to evolve, MLPs are finding their way into even more industries, from personalized education, tailoring learning materials to students, to robotics, helping machines interact with their environment. So, what's the takeaway? MLPs aren't just theoretical. They're transforming the world around us. They're predicting what you'll watch, keeping your money safe, improving healthcare, and even helping machines understand human language. But here's the thing. MLPs aren't perfect. Sure, they're powerful, but they still have weaknesses. So before we start celebrating, we need to ask a crucial question. What are the biggest challenges when training an MLP? Because trust me, even the best neural networks can struggle if we're not careful, and some of these challenges might surprise you. Now that we've seen how MLPs are being used in the real world, let's take a step back and ask, why are they so powerful? What makes MLPs different from traditional machine learning models, and why do they dominate so many AI applications? The first big advantage is their ability to learn complex nonlinear patterns. Unlike simple models that can only handle straight-line relationships, MLPs can recognize intricate patterns, relationships, and hierarchies in data. Think about it, data in the real world is messy. If you tried to classify emails as spam or not using just a few simple rules, you'd fail miserably. But MLPs can process thousands of features, detect hidden connections, and build a sophisticated understanding of the data. Then there's their flexibility in architecture. You can customize an MLP in countless ways, adjust the number of layers, tweak the number of neurons per layer, change activation functions, fine-tune hyperparameters. This means MLPs can be tailored for a huge range of problems, from image recognition to financial forecasting. Whether you need a simple 3-layer network for quick classification tasks or a deep network with dozens of layers for complex AI applications, MLPs can be adapted to fit the need. And let's talk about their universal approximation power, the ability to approximate any function given enough neurons and layers. This is huge because it means that, in theory, MLPs can model any relationship in data. Whether it's predicting weather patterns, identifying fraudulent transactions, or even learning the complex structure of human language, an MLP can be trained to do it. Another major advantage, they work well with both structured and unstructured data. Traditional machine learning models work best when dealing with structured data like spreadsheets, columns of numbers with clear relationships. But MLPs can go beyond that, handling unstructured data like images, audio, and text. This is why they power everything from speech recognition to handwriting detection to chatbots. And let's not forget scalability. MLPs can handle large amounts of data and improve as they receive more examples. The more data you feed them, the better they get. This is especially useful in areas like personalized recommendations, where the system continuously improves as it learns more about user behavior. Finally, there's the fact that MLPs are self-improving. Unlike traditional rule-based systems, which require human experts to manually define decision-making rules, an MLP learns directly from data. Once trained, it can adapt and refine its knowledge without human intervention. But before we start thinking MLPs are unstoppable, let's be real. They come with challenges too. Sure, they're powerful, but they aren't always easy to train. They require large datasets, tons of computational power, and careful tuning of hyperparameters. And if you're not careful, they can overfit, become too complex, or even get stuck in training. So while MLPs are incredibly powerful, we need to ask, what are the biggest challenges in training them? Because as much as they can do, they still come with some serious hurdles. And that's exactly what we're going to tackle next. Awesome. We've talked about how powerful MLPs are, how they can approximate any function, and how they're being used in the real world. But now it's time for some real talk, because while MLPs are great, they aren't easy to train. In fact, there are some major challenges that can turn even the best designed network into an absolute disaster. First up, the vanishing gradient problem. This happens when a network is too deep, and by the time the error signal reaches the early layers during backpropagation, it becomes so small that the first few layers barely learn anything. It's like trying to send a message through a long game of telephone. By the time it reaches the first person, it's completely garbled and useless. This is why deep networks often need special tricks like ReLU activation functions, batch normalization, or residual connections to keep the gradients from disappearing. Next, we have computational complexity. Let's be real, MLPs are resource hogs. The deeper the network, the more calculations it needs, which means more processing power, more memory, and longer training times. Training a large MLP on a standard laptop? Forget about it. That's why deep learning relies so much on GPUs and TPUs, which can handle the massive number of matrix multiplications required for training. Another challenge? the need for large data sets. MLPs are data hungry. They need a lot of labeled examples to learn meaningful patterns. Unlike traditional machine learning models, which can sometimes get away with small data sets, MLPs require thousands, if not millions, of examples to perform well. And if the dataset isn't large enough, you risk overfitting, where the model memorizes the training data instead of actually learning patterns. Speaking of overfitting, that brings us to the next problem, generalization. Just because an MLP performs well on training data doesn't mean it will do well on new data. If the model learns too many details from the training set, it won't be flexible enough to handle unseen examples. That's why we use regularization techniques like dropout, L2 regularization, and early stopping to keep the model from becoming too specialized. And finally, hyperparameter tuning. There's no magic formula for picking the right learning rate, batch size, number of layers, or neurons per layer. It's a trial and error process, often requiring techniques like grid search, random search, or Bayesian optimization to find the best settings. Get the hyperparameters wrong, and your model might learn too slowly, overfit, or fail to learn at all. So, what's the takeaway? Training an MLP is a balancing act. If it's too shallow, it won't learn complex patterns. If it's too deep, gradients vanish, computation costs skyrocket, and overfitting becomes a real threat. And without enough data, the whole thing falls apart. But don't worry, MLPs aren't the only game in town. In fact, for some tasks, other types of neural networks perform way better. For example, if we're dealing with images, wouldn't it make more sense to use a network designed specifically for visual data? Well, that's exactly why convolutional neural networks, CNNs, exist. And trust me, if you think MLPs are impressive, CNNs will blow your mind. Let's dive into that next. Yeah, we've spent a lot of time talking about MLPs and how they can approximate any function, which sounds amazing, right? But here's the thing. MLPs aren't always the best choice for every problem. And nowhere is this more obvious than when dealing with images. Imagine you're designing an AI to recognize handwritten digits. If you used an MLP, you'd have to flatten the entire image into a single row of numbers before feeding it into the network. This means the model loses all spatial relationships. It treats pixels at the top left the same as pixels at the bottom right. That's like trying to recognize someone's face by looking at a random list of their facial features instead of an actual picture. This is where convolutional neural networks, or CNNs, come in, and trust me, they are game changers for computer vision. Unlike MLPs, CNNs are designed to process images the way humans do. Instead of treating each pixel separately, they use special filters to detect edges, textures, shapes, and patterns, just like your brain does when you recognize a face. An MLP is like an overly literal person who tries to memorize everything. Show them an image of a cat, and they'll remember every pixel exactly. But the moment you change anything, the angle, the lighting, the size, they get completely confused. CNNs, on the other hand, focus on key features. They look for whiskers, ears, fur texture, and they still recognize the cat even if the image looks a little different. CNNs work by scanning an image with small filters, learning to detect patterns that get more and more complex at each layer. Early layers detect simple edges and corners, middle layers recognize textures and shapes, and deeper layers put everything together to identify entire objects. This step-by-step approach makes CNNs incredibly effective at understanding visual data, far beyond what an MLP could do. And here's the best part. CNNs require way fewer parameters than MLPs because instead of trying to memorize every pixel, they share their filters across the entire image. This makes them much more efficient, meaning they can train faster and perform better even on large-scale image recognition tasks. So what's the takeaway? If you're working with data that comes in tables or spreadsheets, an MLP might be fine. But the moment your data has a spatial structure, like images, videos, or even some types of sensor data, CNNs are in a completely different league. But wait, what if the data isn't spatial but sequential? What if we're dealing with speech, time series, or natural language? That's where another type of neural network comes in, recurrent neural networks, or RNNs. And trust me, if you thought CNNs were cool, RNNs will blow your mind. Let's dive into that next. Great. By now, we know that MLPs are powerful. They can recognize patterns, approximate complex functions, and power everything from image recognition to recommendation systems. But there's one thing they struggle with: time. Think about how humans process information. If I tell you a sentence word by word, you don't just treat each word independently. You remember what was said before, connect it to what's being said now, and predict what might come next. This is where MLPs fall apart. They process everything as a fixed input, meaning they have no memory of what came before. They look at words in isolation, treating every input like it's brand new. And that's a problem if we're dealing with sequences like speech, text, or time series data. This is where recurrent neural networks, or RNNs, come in. Unlike MLPs, RNNs have a built-in memory system. They aren't just looking at the current input, they also remember previous inputs, allowing them to learn relationships over time. Instead of just analyzing one word or frame at a time, RNNs process sequences by passing information from one step to the next, updating their understanding as they go. Imagine reading a book. If you only focused on one word at a time without remembering the previous ones, the story wouldn't make any sense. RNNs solve this by maintaining a hidden state that carries information from past inputs. This makes them ideal for tasks like speech recognition, language modeling, stock market prediction, and anything else where context matters. But here's the catch. Standard RNNs struggle with long-term dependencies. As the sequence gets longer, the network starts to forget earlier information, leading to a problem known as the vanishing gradient issue. If you've ever tried to remember a phone number for too long and eventually lost track, that's exactly what happens to an RNN trying to process long sequences. To fix this, researchers develop more advanced versions of RNNs like LSTMs and GRUs. These architectures have special gating mechanisms that decide what to remember and what to forget, making them much better at handling long-term dependencies. That's why they power things like machine translation, chatbots, and predictive text, applications that need to understand full conversations rather than just isolated words. So where does this leave MLPs? If your data is static, structured, or doesn't have a meaningful sequence, an MLP might be enough. But if your data has a time component, if past inputs influence future outputs, an RNN is usually the better choice. And now that we've covered MLPs, CNNs, and RNNs, the next big question is, what's next? AI is evolving fast, and new architectures are pushing the boundaries of what's possible. Let's take a look at where MLPs are headed in the future and how new innovations are making them even more powerful. We've covered how MLPs work, their strengths, their weaknesses, and how they compare to CNNs and RNNs, but here's the real question. Where are they headed next? Because AI isn't standing still, and MLPs are evolving in some seriously exciting ways. One of the biggest trends is dynamic layer configurations. Instead of building a fixed network and hoping for the best, researchers are developing architectures that adapt based on the complexity of the problem. Think of it like a self-adjusting camera lens. It changes focus depending on what's in front of it. This allows neural networks to be more efficient, using only the resources they need instead of overloading on unnecessary complexity. Another major innovation is transfer learning for MLPs. This technique has already revolutionized deep learning in CNNs and NLP models, allowing networks to be trained on massive data sets and then fine-tuned for smaller specific tasks. Instead of starting from scratch, MLPs can now leverage pre-trained models to learn faster and with less data, making AI more accessible to industries that don't have millions of examples to train on. Then there's the rise of attention mechanisms. Originally designed for sequence models like transformers, attention layers are now being incorporated into MLPs to improve feature selection. Instead of treating all inputs equally, attention allows the network to focus on the most important parts of the data, filtering out noise and improving accuracy. It's like highlighting key sentences in a book instead of reading every word with the same level of focus. Another exciting direction is multimodal learning, where MLPs are being integrated with other architectures to process multiple types of data at once. Imagine a system that can take text, images, and audio simultaneously, learning how they connect. This is already being used in AI assistants where speech recognition, language understanding, and image analysis all work together in a single system. And let's not forget real-time processing. With advances in hardware, MLPs are becoming fast enough to power real-time applications like autonomous vehicles, real-time fraud detection, and instant language translation. These networks are being optimized to run efficiently on mobile devices and edge computing systems, reducing the need for massive cloud servers. But perhaps the most important shift is in regularization and optimization techniques. New methods like dropout, batch normalization, and weight pruning are making MLPs more resilient, efficient, and scalable. These improvements are allowing deeper networks to train faster and better than ever before, reducing the traditional barriers of computational cost and data requirements. So, what's the big picture? MLPs are not just staying relevant, they're evolving. With smarter architectures, transfer learning, attention mechanisms, and real-time capabilities, they're becoming more powerful and flexible than ever. They may have started as simple function approximators, but they are now stepping into roles that were once thought to be exclusive to more complex architectures like CNNs and transformers. And now, with all this in mind, it's time to wrap things up. Let's take one final look at what we've learned and why MLPs continue to be a foundational tool in the AI revolution. We've covered a lot, from understanding how MLPs work to exploring their real-world applications, their limitations, and how they compare to CNNs and RNNs. It's clear that these networks remain a fundamental pillar of artificial intelligence. At their core, MLPs are universal function approximators. They can learn any pattern in data, given enough layers and neurons. Their strength lies in their ability to process structured data, recognize complex relationships, and adapt to a wide range of tasks. That's why they're still widely used in fields like finance, healthcare, and recommendation systems. But we've also seen that MLPs aren't always the best tool for every job. When dealing with images, CNNs offer a more efficient solution. When processing sequential data, RNNs and transformers outperform MLPs by incorporating memory and attention mechanisms. AI is all about choosing the right tool for the task, and MLPs, while powerful, have their limits. We explored the biggest challenges in training them, vanishing gradients, overfitting, computational costs, and saw how techniques like dropout, batch normalization, and modern optimizers are helping overcome these issues. The future of MLPs is being shaped by new advancements, from adaptive architectures and multimodal learning to transfer learning and real-time processing. So where does this leave us? MLPs might be one of the oldest neural network architectures, but they are still evolving. They continue to be the foundation for many AI applications, and with new optimizations, they remain highly relevant in today's deep learning landscape. This is just the beginning. AI is moving fast, and the more we understand these models, the better we can use them to solve real-world problems. Whether you're building an AI model, optimizing neural networks, or simply curious about how these systems work, one thing is clear. MLPs are here to stay, and their journey is far from over.